Hello everybody, my name is Izzy. I'm a research associate at Create for STEM, and I'm here to introduce you to the Crafting Engagement in Science Environment project. During this talk, I will give a brief introduction of the project, go over the design principles used to design the curriculum. I will give you a short glimpse of the units. We can discuss some research results, and at the end, I will bring about some questions and discussions that came about when discussing this with different teachers and districts. So to understand the background of this project, we first have to consider the changes made to science education within the United States. And in 2012, the framework for K-12 science education was published, and subsequently after, the Next Generation Science Standards. The framework and the standards aim to change instruction from learning about scientific ideas towards making sense of phenomena. A term used is knowledge in use. Namely, how can I use the knowledge that I have to make sense of a phenomena or answer an important life question? Our goal was to support teachers in the development of learning environments that enhance optimal learning moments for students in secondary science, physics, and chemistry classroom. And that sentence is quite a mouthful, so I would want to break it down for you guys and let you know exactly what we mean when we say each part of it. So when we say learning environments, our basic criteria was we wanted to design project-based learning units, so we had to use project-based learning design principles. We want students to figure out phenomena, and we want them to use all the dimensions, namely disciplinary core ideas, cross-cutting concepts, and scientific practices, and we want them to promote engagement. If you go back, it's here we wanted to enhance optimal learning moments. So what are those optimal learning moments? The idea here is based on the concept of flow, which is a very well-studied concept in education, whereas if you can hit the right amount of skill, interest, and challenge, students are in the situation of state of flow, namely where they don't feel time passing by and they're so engaged in the activity. And we use that as a framework to measure and understand optimal learning moments. This figure here depicts our basic model of optimal learning moments, including everything that affects optimal learning moment, so that we know what to measure in the study. When we say supporting teachers in developing engaging learning environments, what we really think of it is a system of support. It's not only just the curriculum, it's not just the assessment, it is a system that works together. So in here, these are the main components of the system. It's comprised of 3 physics units and 4 chemistry units, designed using a research-based methods. We also developed post-student assessments. We also spent a lot of time working with the teachers and engaging them with the curriculum itself. And we always employ feedback-based modifications as well as continuous support. And all this system has to work together in unison to get the results that I'm about to show you. When we say learning goals, to be more specifically, we talk about performance expectations, namely how do we intertwine scientific and engineering practices, cross-cutting concept, and disciplinary core ideas in order for students to make sense of a phenomena. Our basic design principle throughout the units and within a unit and within a lesson is this cycle depicted here. Namely, we want students to experience a phenomena, which leads them to asking questions, and in order to answer those questions, they need to use scientific practices. They need to ask questions, they need to design an experiment, they need to measure, and once they do that, they figure something out. It might not be the whole answer, but it's a step forward. Normally, figuring something out will also uncover new questions that you have to answer, and new phenomena that you experience, which continue the cycle throughout. And that is the basic experience we want students to have as they go through a lesson, as they go through a unit, and as they go through a sequence of units. This figure shows the design process for our units and our assessment. And I don't want to get into the unit, I don't want to get into this figure. I just want you to show that we have a systematic way of starting from a performance expectation all the way down to assessment task, denoted here in green, or an actual curriculum in blue. That means that we can take NGSS performance expectation, work in a very ordered, organized, research-backed method to slowly unpack it and build a task that's aligned to it, as well as a curriculum that aligns to it. And that is what guides us through this project. So, like I mentioned, we developed 3 physics units and 4 chemistry units. The topic for each unit is shown here in this slide. The top 3 are the physics units and the bottom 4 are chemistry one. For everyone, so for example, forces in motion, which is the first physics unit, the driving question, namely the question that leads the investigation, is how can I design a vehicle to be safer for a passenger during a collision? The phenomena the students focus on is car or cart collision, and the PEs covered are denoted here in the last column. So for every unit, we have a driving question for the unit, an anchoring phenomena for the unit, and the associated PEs. You would notice that in some units we cover more PE than others. That's because of every PE is not created equal. Some PEs have a wider scope than others. So for example, the conservation of mass is its own unique PE. Therefore, there's only one performance expectation there. When we developed this teacher guides, we had to balance out a few things. We wanted the teacher guide to be instructive and very complete, but we didn't want them to be scripted. Namely, we didn't want teachers being told what to do at every specific point. Rather, provides a framework for them to work within. The compromise in between led to a very detailed teacher guide that's around 50 pages per unit. And like I said, it's not a script, but it's not also not a standalone product. That does not mean to say that they're incomplete or that they're not good. But like I said before, they're part of a system that works together. So I can show you a little bit of the teacher guide. So this is an example of the evaporative cooling teacher guide. And as I scroll down here, you can see here, let me zoom down just a little bit. You can see here the lesson sequence for every lesson. So every unit is typically around 10 lessons. Should take 4 weeks of instruction. And when I say should, these are estimated times. We would say somewhere between 3 to 4 weeks, giving a 50-minute-ish time block. So if I scroll down through the unit, and again, this is not meant for me to read this to you, I just want to show you the level of detail put in the unit. So we have a unit overview of the PEs covered, very extensive, some background for teachers, background for students, prerequisite knowledge for students. This part is crucial when you guys are trying to figure out where to put the actual unit within the sequence, so we know what students need to know when they come in. Some of the units are also associated with an online activity at the Concord website, which is a free to use, no charge website that provides access to the units as well as embedded simulations and activities. Highly recommended. To go over how a single lesson looks, so every lesson has its lesson level driving question, a summary, the learning goal for the unit, students figure outs and look fors, which are and evidence statements, as well as materials and preparation. Every lesson has also a suggested time sequence, and I want to emphasize that it is suggested. Like I said, this is not a script. This is kind of our way of giving some numbers behind the activities, but we encourage teachers to find their own pace and put more emphasis or less emphasis on different parts as they see fit. And then we start with the learning sequence itself, and the unit itself also has a link to students' sheets that, if needed, are also part of the teacher guide. And this is the end of lesson 1. Right? As I scroll down, lesson 2 has exactly the same structure: summary, learning goal, preparation, time suggestion, and the actual sequence itself. So those are the teacher guides, and we have a teacher guide for each and every unit. So if I go back here, so there are a total of 7 teacher guides with associated student sheets that are available with this project. Now, the research part. And this is a very ambitious project because our goal was to provide empirical evidence to answer the question whether this curriculum actually works. More specifically, we're trying to ask, does this system, which involves curriculum, assessment, teacher support, research-backed design, actually improve students' learning and social and emotional disposition? Namely, are students more engaged or less engaged in the curriculum? And the only way to provide large-scale quantitative data is to run a scientific design structure. So the design we chose was a cluster randomized design. And for those who are not familiar with it, I'll elaborate just a little bit. A cluster randomized design means that we selected a sample of schools to be in the study. Those schools were randomly chosen to be either a control school or a treatment school. And the treatment school were giving our curriculum and system of support, whereas the control schools did not. They just went about their daily business. And we measure the students' performance at the beginning of the school year and at the end of the school year. And when we try to compare the students using a matched design. So the results I'm about to show you, they come from a 1 year of data collection. This whole project is a 5-year NSF grant. Just for 1 year, the numbers are 70 schools, 130 teachers, and about 6,200 students that span a very wide ethnic and socioeconomic background. So we are really trying to make we're trying to make a very wide statement here. We're not measuring 1 or 2 classrooms that can be accused of bias because it's a specific type of students. Not at all. We are trying to empirically answer the question, does this system work? So these are all the measures that we had to develop in order to make sure that we are actually capturing the difference stemming from the system of support rather than an outside confounder, be it students' prior achievement, student level of ability, ethnic background, socioeconomic background, and many more. So when we develop all these surveys and units and assessments, we have to put them in some sort of a structure. And this is the structure that we use. So let me go over this slide just a little bit to kind of walk you through this. So the blue line represents the school year. And movement along the line is basically time throughout the school year. So the left edge of the map is the line is the start of the school year, and the right edge is the end of the school year. So we had control teachers or control schools or control classes, whatever you want to call it, and we had interventions. And at the beginning of the year, we gave pre-summative tests, which are tests that we did not devise, which are pre-sanctioned, validated items. For this example, we used NAEP items to establish students' baseline ability, namely how proficient they are in science when they start the school year. And then the intervention schools gave our units. They note here with like these 3 marks, green marks. It's 3 because I was showing here the physics one, but if chemistry, there was another one here to denote 4 units. And the control schools or teachers or classes just went about their life. And at the end of the year, we gave the same test to the intervention schools and the control schools. Again, not a test that we designed, not a test that we kind of constructed, but rather an outside validated test to measure student science proficiency. In our specific case, it was M-STEP items. So actual items from the new version of the NGSS aligned M-STEP to measure students' performance on and GSS aligned tests. In addition to that, if you can denote it here by the light green arrows, we had for every unit, we had post-student assessment to measure how students perform on each of the units. And we also have ESM measurements, which I will go back after I'll show the results. So when I say social and emotional learning, again, those yellow marks, we're really trying to figure out how do we measure students' engagement. And we decided that the classical survey at the end of the unit and at the beginning of it is not going to cut it. Mainly because students are not that uniform. You cannot measure engagement on such a wide scale. What we suggested is a different method that captures the in-the-moment engagement of the student. Literally when they are doing the units, when they're in classroom, when they're outside of classroom, so that we can basically calibrate the engagement level based on the students. And to do so, we actually gave students smartphones, deactivated smartphones that had a 90-minute survey on them that beeped, namely barked, because it's like a dog. It barked when they were in their prior units, it barked when they were not in their prior units, and they barked when they were outside of school. And they had to fill a very simple survey that asked them about their social and emotional construct. What are you doing? Are you interested in? Do you feel skilled? Do you feel bored? How important this is to you? And doing so allowed us to actually capture the inherent fluctuation in students' engagement even throughout a day. To show you an example, this is one student's results reporting on imaginative thinking, namely how much are you using your imagination in your work. The gray highlighted parts are our units, namely our physics units, and the white parts are the, for the lack of a better word, the regular teacher instruction. So we measure the student when they were doing our units, but also when they were doing their teacher's regular units. As you can see here, there's a fluctuation between the reported imaginative thinking for the student in and out of prior units, which also provides more evidence to does this system of support actually helps with students' engagement. And again, so those are the ESM measurements that were done both for the intervention and the control. And if we want to go back to the actual results, namely, let me go back here, the difference between the pre-summative test and the post-summative test matched by their initial performance. Namely, we didn't compare high ability students from low ability students and vice versa. We took the same ability students as measured by the pre-summative test and compared their performance on the post-summative test between students who did experience the prior system and students who did not. And the left panel shows that. The red line at the bottom denotes the control calibrated at 0. And this is the performance of the intervention schools or students at the post-summative test. Again, matched and calibrated. So we can see here that our students perform almost a quarter of a standard deviation better than the controlled schools. That means that we have clear, large-scale empirical evidence that engaging with our system of support, namely the curriculum and the professional learning and the assessment and the constant support with the teachers, actually improves students' performance at a third-party assessment item, namely the M-STEP, which is a very big and significant result that not a lot of studies can claim. But that wasn't enough for us. We wanted to say, well, we were worried because we said maybe it's only the top tier students who gravitate towards this type of system. Maybe they're the one who are improving, and that's what's pulling the average above 0. So what we did is we took the sample of our intervention students and we divided them up to tertials, basically based on their performance at the pre-test. And we said, let's see how much each tertial is actually improving. and that's the panel on the right. So as you can see here, you can see that that the most improvement was actually not for the top tertial, marked here in yellow/orange. It was actually for the bottom third of the students, namely the students who performed the lowest at the pretest were actually the one who gained the most from this units, which is a phenomenal result because it means that we are not catering to the high ability students. We actually cater to all students, but we put extra emphasis, or this system put extra emphasis on the bottom tertial students, the students who are behind on the ability scale. So we find that result amazing, and it's part of why we're so proud of this curriculum. So to summarize this presentation, we've actually developed a system of support that works. And I can say that it works, and I can even put an exclamation mark at the end of it, because we have large-scale empirical cluster randomized data to support that. And we can show that students improve in their social and emotional construct, namely their engagement, as well as improving their learning. This shows the potential of PBL, or project-based learning, as a framework to promote those things in the NGSS era. And what we also show here, that if we approach this in a systematic and research-based methods, we are able to achieve results with teacher professional learning, curriculum, and assessment. And that is all that I have to share with you today. If you have any additional questions, feel free to contact any of the people mentioned here. You can contact me. You can contact the Next Generation Project-Based Learning leader, which is Dr. Chris Ryman. And if you're from the Oakland ISD, you can also contact your ISD person, which would be James Emerling, at this email. Thank you.